noncommutative geometry, just in completely general terms, not to do with quantum theory to begin with. So the subject begins with the observation that there's a rough equivalence, a contravariant equivalence, between topological spaces and commutative algebras over the complex numbers. So the most precise and relevant form is the Gelfand theorem, which says that compact topological spaces correspond precisely to commutative complex C-star algebras. So I'm not concerned with the details, so don't worry about what a C-star algebra is, except that it is rather important that the algebras in this theorem have a star, they have an involution, but I won't talk about that now. All we need to know is that the general idea is that when you have a space X, you take this to the continuous functions on X. And going the other way, when we have an algebra, we take this to some kind of spectrum of the algebra, which you can think of either as the algebra homomorphisms into the complex numbers, or more relevantly, as the space of irreducible A modules. You see, being commutative, all the irreducible modules are one-dimensional, so they correspond to things like that. Doesn't matter for the moment, but because I want to make use of it later on, let me just mention one technicality. Supposing we took, here I mean unital algebras, but supposing I took non-unital algebras, so ones without a 1, they correspond to locally compact spaces. Where given a locally compact space X, we take this to the functions vanishing at infinity. That little naught is meant to mean that the functions vanish at infinity. And that's, of course, an algebra without a 1. So the general idea is going to be, if we have this nice correspondence, obviously we could generalize these things to non-commutative algebras. And they should correspond to some more general kind of thing than a topological space. So they should correspond to something. Well, so non-commutative geometry is sort of the theory of this. Now, why would we be interested in that? I think there are three kinds of motivations. The first one, which I'm not really going to talk about at all, is the fact that if you're actually an algebraist and you're interested in commutative algebras, then it helps a great deal to think geometrically, that it helps to associate to the space this spectrum of its maximal ideals or whatever, and to use geometrical ideas in analyzing the commutative ring. So that's the first kind of motivation, and that's not really relevant to this talk. The second kind of motivation is the one that's mainly associated with Alain Connes, where he is interested in producing things which are a bit more general than ordinary topological spaces. So the kind of examples he's interested in, so he actually wants to generalize topological spaces. And the kind of example he's interested in is usually some kind of badly behaved quotient space. So we have something like the space of leaves of a foliated manifold, or the space of orbits of a group which acts ergodically on a space. For example, supposing we take the circle and we act on it by the group by taking, think of them as complex numbers of modulus 1 by z going to e to the 2 pi I alpha, where alpha is some irrational number, then each orbit is dense. So if we were to try to look at the space, the functions on the space of orbits, they'd be presumably continuous functions on the circle invariant under this action. Well, you'd only have the constant functions, and that wouldn't be very interesting. But Kohn observes that in a situation like this, you can make an algebra, which in this case would be the group algebra of the group. Let's call that G. It's a discrete group. We could take the group algebra, but with coefficients in, let's say, the C infinity functions on the circle. And it then happens that you can easily see that the orbits of this correspond exactly to the irreducible modules for that non-commutative algebra. So one way of looking at that is to say, you might think, well, what's the good of that? Here we have these orbits. There is a nice set, maybe, but they don't have any topology. They sort of all glued together. Well, we can say they're the space of irreducible representations of this non-commutative algebra, but those irreducible representations are all glued together too, so what have we achieved? But we have achieved something, because you see, suppose you have a module M, so that's like a point of the non-commutative space, then you see the algebra acts in it. So if we take any element of the algebra, it acts on this, and we get a matrix. So Kohn's perspective is that although we don't have any scalar valued functions, we do have lots of nice functions which are matrix valued and hence form the non-commutative algebra. Well, even so, what do we do with this? So let me now mention very briefly the third motivation, which comes from quantum theory. I said in my first lecture, in quantum theory the world is presented to us as some kind of non-commutative algebra, and when we want to understand what the world actually looks like, we think that the world we want to interpret in terms of some kind of classical phase space, so we want to associate to this non-commutative algebra a space. We want to think of it geometrically. So in what sense, all the same, can we think of this unpromising space of leaves or orbits or something in some geometrical way? So what Kohn did was to assign to a non-commutative algebra the kind of invariants that a topological space has, which don't change under deformation, so homotopy invariants. So Kohn's project was to assign things like cohomology, K-theory to the ring. So they're invariants of its homotopy type. So let's ask a apparently more modest question. Instead of thinking of an algebra as defining a space, a non-commutative algebra, can we think of it as having at least a homotopy type? Well, again, the answer is no, but I want to explain that a little bit carefully, because you might at first think the answer was definitely yes. The point about a homotopy type is that it's extremely robust. In my lecture, my lecture about the Madsen-Tillman work, I explained that the space of d-dimensional manifolds has a very good homotopy type, even though there are many different realizations of it as a space. But the homotopy type is robust. And so the thing to bear in mind when you have a space is that if you're interested in it up to homotopy, you can reconstruct the homotopy in a lot of very apparently combinatoric and discrete ways. For example, you can consider the category of all, let's say, contractible open subsets of X. That forms a category, and a category defines a topological space in a straightforward way, and the homotopy type of that category of contractible open sets will recover the homotopy type of the actual space X. But you can also take, for instance, all sufficiently small open sets, or you could take the category of singular simplexes with inclusions of faces, or you can take the category of all spaces mapping into X and then take some kind of limit filtering the category. Anyway, there are lots and lots of ways you can make the homotopy type. It's very robust. And of course, the famous achievement of Grothendieck was that, still working with a commutative ring, he defined a notion of sufficiently small open set for a commutative ring, and by considering the space of that category, Grothendieck assigned a homotopy type to any commutative ring, which in the case of a C-star algebra would still give you the same homotopy type as the topological space, and that enabled him to give homotopy types to things like the ring of integers or an algebraic number field, all sorts of things which have intricate homotopy theory, even though if you were to consider the actual rather horrible set of their maximal ideals, you would see nothing at all of a geometrical nature. Well, so we ask this question, can we define a homotopy type for a non-commutative ring? Con's examples would lead you to think that you could, because at least most of all of his sort of primary examples, as I said, come from taking a space with some kind of equivalence relation on it. So actually one has a groupoid, one has objects, and one has isomorphisms between the objects, being in the same orbit or whatever. Well, a groupoid is a category, and a category has a homotopy type. So spaces like his Z acting on the circle and so on, that has a homotopy type. In fact, in that case of Z acting ergodically on the circle, it's just the homotopy type you get will be a torus. Well, I won't talk any more about that now, but all of Con's basic examples do have a homotopy type. So why don't we always have a homotopy type? Well, the first clue is to see that it's clear that the points of this space, being the modules, what we're focusing on is the category of modules for the algebra rather than just the irreducible modules. So we're led to look at something a bit bigger, the class of all modules. We in fact need to do that because a typical non-commutative ring won't have any irreducible modules at all. One of the famous examples is the one which Con associates to the space of Penrose tilings of the plane, where you have an algebra where the modules for the algebra correspond to pairs of positive integers m and n, such that m plus n alpha is positive, where this is the golden ratio, whatever that is, square root of 5 plus 1 over 2, some irrational number. Well, so the modules correspond to all the irrational numbers of this form which are positive. There clearly isn't a smallest one, and direct sum corresponds to adding this number, of course. So very often there aren't any irreducible modules, and you have to consider all the modules. Well, so we decide that we're interested, the geometrical object is not so much the ring as its category of modules, and that means we're considering rings up to what is called Morita equivalents. That's just a definition. Two rings are called Morita equivalent if their additive categories of modules are equivalent additive categories. Well, so now we get a clue to this question of homotopy type, because suppose we think in terms of the rings for a moment. If we're interested just in the ring up to Morita equivalence, then a ring is equivalent to the ring of matrices of any size over it. We don't distinguish between, say, B and the ring of 2 by 2 matrices over B, because the category of modules of these two things are the same. On the other hand, suppose we have two homomorphisms of rings like this in our category. Well, then we have a natural way of adding them, because we can think of the homomorphism which I write schematically like that. And this will be a homomorphism thus. And we can think of that as the sum of the two maps. So homotopy types of so classes of maps in non-commutative geometry should be able to be added. It's not clear they can be subtracted, but in fact it's convenient to make a category in which they can be subtracted. Now, if we start with so we think, could we possibly associate to a non-commutative ring a homotopy type? Well, it would seem not, because there's no way of adding homotopy classes of maps between spaces. So supposing we consider let me, for compact spaces x and y, write this for the homotopy classes of maps. Well, there are various well-known ways of making this, of enveloping this in an additive category, and I'm going to mention just three very quickly. The first one I'm not really going to say anything about. This is the stable homotopy category, beloved of algebraic topologists, where a map is a map from this to this in this category. It's a map from a suspension of that to a suspension of that. There's another one that I'll come to, and the third one, which I'll call h of xy, is somehow the crudest way of forcing oneself to be able to add maps. You see, if you want to add two maps, then presumably what you get is some kind of many-valued map. What's the crudest kind of many-valued map you could have? Well, supposing you, let's say, C sub y, no, sorry. Let's take Z sub y to be the free abelian group generated by y, the space y. So just regard y as a set and take the free abelian group, but the topology of y induces a natural topology on that. So that's a topological space. And you can think of a many-valued map in the crudest sense. A many-valued map from x to y is a map from x to z of y. So let's consider the homotopy classes of maps from x into y, x into z of y, sorry, and call that the homotopy classes of many-valued maps. So that's the crudest way of enveloping this in something additive. Now there's one, and it factors through this. There's one in between, which I'll call little k of x and y. So this is stable maps. And this is the maps, the homotopy classes of maps of x into something that I'll call little k of y, where little k of y is the space of finite length C of y modules. Now, what is a finite length C of y module? Well, you see, it's a finite dimensional vector space V on which this algebra acts. Well, being a commutative algebra, well, I'm going to be slightly sloppy. Being a commutative algebra, let's suppose we can diagonalize this action, so we can write all the actions as the action of A as a diagonal matrix depending on A. Then clearly each of the lambdas will have to be a character of A, an algebra homomorphism from the ring. That will be a point of Y. So a point of this space, if this is Y, a point of this space is a set of points in Y, each point being somehow decorated with the corresponding eigenspace corresponding to the character which we get at that point. You see, this we really have the action of A decomposes this into a sum of things V lambda, where lambda runs through some set of characters like that. And each character is a point of the spectrum of Y, of the spectrum of C of Y, which is Y. And so we have these points, each labeled with finite dimensional vector spaces.
That's the sum over C lambda, which is character on C of Y.
Sorry, yeah, absolutely. Sorry. Right. So I want to And so you have to give that a topology. The topology allows these points to move. They should all have been called y's, sorry. They're allowed to move around, and they can coalesce, and then the eigenspaces will just add in the obvious way, adding subspaces of the vector space V.
V lambda need not be one-dimensional.
No. You see, because so think of that as a point with a multiplicity. In fact, that's what I was about to say. You see, a point of this space, so we have k of y, and we have z of y. Now, so a point of this is some formal combination. You can think nk, yk, where yk is a point of y, and nk is an integer, positive or negative. A point of this space is a formal combination sigma vk, yk, where again the yk are points of y, and now the v's are finite dimensional vector spaces. So this is a sort of refinement of this space where we, in modern language, categorify the label. Instead of just giving the point a multiplicity which is an integer, we give it a multiplicity which is a vector space. And we can make sense of that with virtual finite dimensional vector spaces too, and that will give us this space. In fact, you can give a similar description of this. This is the maps of X into something usually called Q of Y, where this is the space of virtual, I don't want to explain what that really means, virtual finite subsets of Y. Well, now, the great advantage of this thing is that it's something that makes sense, you see, for any non-commutative ring, because this was the space of something completely algebraic, the space of finite length modules. Now, you might feel a little bit suspicious because finite length modules only make sense for certain kinds of algebra. I mean, if you took, if you're looking at the algebra of bounded operators in Hilbert space or something like that, a finite length module would be a pretty dubious idea. I mean, there wouldn't be any. So, but we'll come back to that in a moment. The thing that we certainly can do, if we want to, you see, is associate to an algebra this space k of y, which only depends on the ring here. So this functor y goes to k of y. That extends to a map from algebras to something which, rather abusively, I'll write. This is k of y if a is the continuous functions on y. And this does have a homotopy type. So this is a homotopy type which we've naturally associated to the ring. And we can look at its invariants, and they are, we can think of those as telling us about the shape of the ring, the algebra A. Now I want to point out one curiosity about this. Before I come to physics and quantum field theory in particular, remember in my first lecture I factorized classical physics into two steps. And the first step I called ontology, and the second step something else. The first step, this ontology, was something which took space-time, or took space really, and associated to space the configurations of states of the universe in classical physics. So if this space was Y, remember these states of the universe were like some configuration space of discrete subsets of points where particles were, maybe decorated with some fields, which were in the spaces in between the particles. So we had this thing, states, well, configurations. Now what I want to point out is that this going from y to k of y has an obvious resemblance to that. You see, we started off with an algebra which was meant to describe y, and we managed to associate something geometrical to it. But the thing that was geometrical wasn't like y, but it was like the configurations of points in y, each point being equipped with some finite dimensional vector space tagged onto it. So that's the first remark, that somehow, well, I'll come back to that later. Now, the next remark is, let's go back to this physics motivation. In physics, we say the world is described by a non-commutative algebra, and we'd like to see that as a space. But the motivation there was to say that our non-commutative algebra is meant to be some small deformation, depending on a small parameter Planck's constant, of a commutative algebra. And remember, I said we think of this quantum universe described by this as corresponding somehow to the classical universe, which was the spectrum in the usual sense of this commutative algebra. So, at first sight, this looks like a radically different way of associating a space to an algebra. You see, in the Kohn picture, to the algebra we considered the space of irreducible modules for the algebra, and here we consider the space of the spectrum of the commutative algebra, of which the non-commutative one was a deformation. Well, that's a very different thing. At least it seems very different. But it's not quite as different as it seems. The difference is closely related to the Bott periodicity theorem. And again, this is one of Kohn's basic observations, which I'm now going to tell you. So this is all explained very beautifully in his great book. But I want to say it in a particular way. Even before saying that, let me say something about these things. These different ways of making the homotopy category additive are not as different. I mean, they look extremely different from their mode of definition. But they're not so different because, for instance, if we tensor them all with the rationals, they're all abelian groups. Supposing we tensor them all with the rationals, well, then we get things which are pretty much the same. In this case, and that's why I use this notation, this will just be obviously it'll be a rational vector space. It's the rational vector space of homomorphisms from the rational homology of x to the rational homology of y, homomorphisms of graded vector spaces. This is the same. And this is almost the same. This is just homomorphisms of even positive degree. So here I meant homomorphisms of graded vector spaces of degree 0. Similarly there. This one is bigger because you allow homomorphisms of any positive even degree. That's sort of saying that we're looking at twofold suspension simultaneously, looking at the space together with its twofold suspensions, at least up to rational multiples.
The top one? What do you mean by same?
Same as this.
I see.
Okay, now Bott periodicity. So Bott periodicity is, in the Kohn formulation, which is very different from Bott's, of course, is the statement that in the non-commutative category, our vector space can take its one-point compactification. So this is, think of it as a locally compact space, the two-sphere we get by taking the one-point compactification of this. That this is equivalent to a point in non-commutative homotopy. Is a deformation of a point. So what do I mean by that? You see, I said that the quantum mechanics motivation makes us want to associate a space to an algebra H which doesn't change when we go between the commutative thing and a non-commutative deformation of it. Now here we have this locally compact space, so let's say it corresponds to the algebra of C infinity functions vanishing at infinity. Now I want to deform that algebra. Well, this algebra of course greatly resembles the algebra of polynomials on R2. So in fact Kahn's observation is that this fact is just a way of stating the Stone-von-Neumann theorem of elementary quantum mechanics, because this resembles the space of polynomials. So think of them as the polynomials in two variables, p and x. And think of deforming these polynomials by introducing a commutation relation that this is I times Planck's constant, where that's a scalar, a small scalar. So when h is 0, we have the polynomial algebra, and we deform it, h being the deformation parameter. Well, as soon as h is non-zero, the isomorphism class of this algebra doesn't depend on h, and it deforms, of course, to the polynomial differential operators on the line, simply by taking x goes to multiplication by x. We replace p by I d by dx, and then a polynomial in p and x becomes a differential operator with polynomial coefficients. So that's this famous deformation, beloved of elementary quantum mechanics. This is, of course, a very similar algebra to this in some moral sense. And when you make this deformation, the way this deforms is this deforms to the operators, the algebra K of R, which is all operators from L2 of R to L2 of R. You see, you can think of these polynomial differential operators as unbounded operators on L2 functions on the line, but because they're very unbounded, so let's this be all operators of the form f goes to let's say k of f, where k of f is something whose value at x is the integral of k x y, or capital K x y, f of y dy, where this is a Schwarz function in both variables. So this is k is a C infinity function tending rapidly to 0 at infinity on R2. So this same deformation becomes this deformation. If you want to make it explicit, you just write the function here as a function of x and x minus y, and then you do a Fourier transform in the x minus y variable. So this is kind of a triviality. On the other hand, this is essentially a full matrix algebra. So in non-commutative geometry, this is a point. So what we have is one parameter deformation of R2. As soon as the parameter is non-zero, R2 is a point. So Kahn thinks of the Bott periodicity theorem as saying that we have this stability under infinitesimal deformation. Well, so if we want to, on the one hand, make the deformation picture coincide with the Kahn picture, and also associate to an algebra a homotopy type that's invariant under deformation, then we have to stabilize this thing, this category in which the morphisms from x to y were this, the homotopy classes of maps of x to y, x to little k of y. We have to stabilize that a bit more so that we don't distinguish between x cross R2 compactified, y cross R2 compactified, and the original space X or Y, as the case may be. So this is what in algebraic topology is called the double suspension of X. So we want to make double suspension be an isomorphism in this category. So that means we have to go to a slightly coarser category still, in which the morphisms from a compact space to a compact space are the homotopy classes of maps of X into something K of Y, where this space you can call various things. I suppose it's traditionally called the Kasparov space of Y. But if you're a string theorist, it's more natural to call it the space of D-branes in Y.
The notation, I don't understand the notation, but it's the same as before.
Yeah, so...
That's little k and capital.
Yeah, that's the little k and that's the capital K. So let me say what this is. You see, a point of little k of Y, as I said, was a finite set of points, each labelled with a finite dimensional vector space. Well, if we're going to do something which is going to cure twofold suspension, then what do we have to do? Well, we have to not just have points, but we have to allow submanifolds, not just naught-dimensional, but of every even, because it's only double suspension we want to kill, any even, I can't draw this, we want to have some two-dimensional things and some four-dimensional things and some six-dimensional things and so on. And each of the, just as these were labelled with finite dimensional vector spaces, so these submanifolds will be labelled with complex, finite dimensional complex vector bundles, possibly virtual complex vector bundles, but I'm going to suppress the virtual aspect of it. And I'm also not going to talk about how these things behave when you when they collide. You see, when these things collide, you just add the labels, but when these branes collide, you have to think a bit harder, and that's why this Kasparov category is hard to define. But anyway, the essential thing is that there is a Kasparov category that you can, this space, the process of assigning to Y, K of Y, which I've defined rather in a cavalier way, this clearly only depends on the function C of Y, but it also makes sense if we replace this by a non-commutative algebra. So we have this procedure which associates to a non-commutative ring a strange space, which I'll call the space of D-branes in Y, if the ring you started with is a ring of continuous functions on Y. Or better still, C infinity functions.
First of all, these bundles don't have connection.
Well, see, I'm doing homotopy theory, so even if they did have a connection, you wouldn't see that.
But you care about the topology of the bundle.
You absolutely care about the topology. And see, one of the many ways in which I've been cavalier in this lecture is I started talking about continuous functions, and here I talked about C infinity functions. And actually, if you really read Kahn's book, he is equally cavalier, because he starts saying he's going to define this cyclic cohomology, but of course the cyclic cohomology of the ring of continuous functions is zero. It's really only the C infinity functions that have cyclic cohomology. And I feel that that would take us back to yesterday's lecture, but the focus of my approach is that I am automatically driven into things like the C infinity functions, even if I'm always driven into things which have nice local smoothness properties, even if I started off with things which weren't. So that's why I'm skating over that point.
What's the definition of capital K sub A for general algebra?
So you have to read the works of Kasparov. But you see, let me say it like this. You see, little k of A is modules of finite length A modules. Okay? So what is capital K of A? A bit schematically. So the version of the definition I'm giving you now actually was given by Michael Atiyah, and Kasparov then kind of worked it out in more detail. So you see, this finite length is not very good. Also, we would like to have virtual ones. We'd like to have negative ones. And also somehow we'd like to build in Bott periodicity, all in one thing. So we'll consider Hilbert A modules with a Fredholm, pairs of Hilbert modules H0, H1, so Hilbert spaces on which A acts, with a Fredholm operator T from H0 to H1. Now, supposing that Fredholm operator actually was literally a map of modules, then in that case the kernel and co-kernel would be finite dimensional modules, and they would be of finite length. So if I made this exactly a map of modules, what I would have achieved is I would have replaced finite length modules by virtual finite length modules. But in this definition, you don't require T to be a map of modules, but you require it to be approximately a map of modules. You ask for the condition that the commutator of T with multiplying by something in the algebra is compact or small or something in some sense that we won't go into. So you make it only commute approximately, and it's in that approximately that you build in this deformation invariance, and hence you build in the Stone von Neumann theorem, which is the conversion of Bott periodicity, and that's what that is. Okay, so what was I going to say next? So let me mention yet another thing about, let me say a little tiny bit more about this. You see, I'm tremendously stressing this fact that we started off with something describing y, and we output something like k of y, which describes more the state of all things in a universe where the space of the universe, the space-time of the universe is y. So that's something that's extremely interesting if you're thinking in terms of how you could make a quantum theory of gravity. Because you see, if you think of the universe just being presented by quantum mechanics, you'll get some big space like this, and the object of quantum gravity is somehow to find the space that it comes from. So now one of the ideas is that this should be somehow made out of some string theory, and string theory is connected with two-dimensional quantum field theories. Now, is the fact that it's connected with two-dimensional quantum field theories, is that just a sort of way of encoding just a certain degree of non-commutativity? Well, one of the first signs that that might be true is if I write down the formula for what this deformation is. You see, we started off with the functions on the plane. In fact, we could have started off with the functions on any linear symplectic manifold, so R2n with its standard symplectic structure. And we're going to deform this so as to get a full matrix algebra. The fact that this is a full matrix algebra is the Stone von Neumann theorem. Well, what is the deformation? Let me just point out to you how to describe this deformation. I just said before we defined it by Fourier transform in one variable, but you can write it in a different way. Supposing we take two functions here, if you like, just think of R2. So take two functions f and g, and we want to define a kind of multiplication which depends on a parameter h. And when h is 0, it will be ordinary multiplication of functions. So we want to say what the value of this function is at a point x. Well, the formula for the deformation is that it's the integral of fy gz dy dz over r2n cross r2n of e to I times the area of the linear triangle with vertices x, y, and z divided by Planck's constant h. In other words, we want to know what the value of this function is at a point x, and we consider varying other points, y and z. We join them by a triangle. Now, because we're in a symplectic manifold, the triangle has an area. We just integrate the two form over that triangle, and that gives us this weighting factor. So we take this thing, which is a sort of combination of, you see, because Planck's constant is very small, this is very highly oscillatory unless the triangle has very small area. So if you imagine this is the stationary phase approximation when the area is 0, we'll just be multiplying, the leading term will just be multiplying the functions in the ordinary way. And on the other hand, as the triangle gets bigger, we'll get an asymptotic expansion which involves derivatives of these functions. But anyway, this is the formula for the deformation. And that's meant to put you in mind of string theory, because if you ask in general, when you have a symplectic manifold, perhaps I better call it M, if you want to deform this and define an algebra like that, then of course there's a tremendous history about how that could be done, culminating in the theorem of Kontsevich of about 10 years ago, who wrote down an explicit, unique asymptotic formula as a formal power series in Planck's constant for the deformed multiplication. And what is Kontsevich's formula? Well, it's exactly this, except that what we integrate over, in general, so we're now in our symplectic manifold M, we want to multiply these things and evaluate at x. Well, we consider all, not just rigid linear triangles, but we consider all curved triangles, all maps gamma from the standard triangle into M, which take the vertices to x, y, z, as in that picture. And we do this, except that the weighting will be, let's just put, suppose the symplectic structure is omega, the two form, we can just write omega of gamma. So when we have a triangle, we integrate the two form over it and call that omega of gamma. We divide that by Planck's constant. This is the same thing as before, the points y and z, which are the vertices. Perhaps I should write y sub gamma and z sub gamma. And we integrate over all these gammas, which take the leading vertex to x. So gamma of first vertex is equal to x. You see, so that's a completely string theoretical deformation formula. And its first sign, you see, that in this very functional analytic thing, just about operators in Hilbert space, when we look at it in some asymptotic sense, we immediately see two-dimensional, we see surfaces appearing. And that's the kind of germ of string theory.
What measure are you using that measure?
Sorry?
When they integrate in the space of such paths, what measure do they use? I mean,
yeah, well, that doesn't have a short answer. I mean, it's all the technology of the only written down treatment that's a bit like this is one by Cataneo and Felder, which is written in sort of standard two-dimensional field theory and what they call the Batalin-Vilkovisky formalism. I find that extremely indigestible, but it's sort of the standard treatment of you write this out in sort of coordinates and you get some Lagrangian and you do all your formulae for perturbative quantum theory on it and you get out the Kontsevich asymptotic formula, and of course it's believed that that's how Kontsevich did it, but his proof doesn't ever mention any measure on the space of surfaces or anything, or even mention surfaces at all. So it's a long story, and it would be certainly interesting to have a better treatment of that than anyone has written down.
Is there any relation between that formal formula with the integral you wrote before? In any sense?
Sorry?
Do you get anything similar when you write down the previous one in R2n? In that case, I mean, when you do it with the fixed parameter?
No, you see, you can think of the original thing with the rigid triangles, the linear triangles, as simply the leading term in the stationary phase approximation to the field theory. You see, if you look at triangles with fixed vertices, then the stationary phase of the integral of the two form will come on the linear triangle, I dare say. And so that's kind of the leading term in the stationary phase approximation. Anyway, so in my remaining 7 minutes, I am going to try and get back to quantum field theory a bit. So I wanted to say that, so in yesterday's lecture I said that a two-dimensional field theory is something like a commutative algebra. Remember I said that if we have a two-dimensional quantum field theory, what do we have? We have a space associated to the circle, and we have, whenever we have a picture like this, a surface, a disk with two holes in it, then this thing, sigma, will give us some multiplication depending on sigma. So we want to think of this as something like an algebra A. And so we have a vector space with a multiplication depending on sigma, which is not either associative or commutative, but is that up to deformation? Because if you want to multiply in the opposite order, you would just move that round, and you can do that by deforming the structure of the surface sigma. On the other hand, you can do it in various different ways. The commuting by going around that way is different from commuting going around that way. Well, we can take a limit, as I explained, and talk about it in terms of the operators at a point, and I also explained it in that language. So in two-dimensional field theory, we have something like a commutative algebra, some generalization of a commutative algebra. Now, what happens, I explained also yesterday that we would like to extend this to three-tier two-dimensional quantum field theories. So what happens then? Then we want to have a point going to a linear category, and we want to have an interval like this, or one-dimensional things going to functors, say from the category at one end to the category at the other end. A circle, this will go to a vector space, topological vector space, and and then the rest of the notation when we have two-dimensional stuff. So if we just look at the data here, then we have this generalization of a commutative algebra. when we add this data, what are we doing? Well, we now have a category here which you should think of as a category of modules for this non-commutative algebra. Well, you certainly should think of it as a category of modules, and this algebra should act on it in the sense that see, supposing we take some object of the category, and let's consider the identity functor, which we will think of as corresponding to a cobordism which just looks like that. Now, supposing we deform this cobordism by a two-dimensional cobordism where we make a hole there. So this is a piece of surface with a hole in it. This will give us a transformation of functors from the identity functor to the identity functor. If there weren't a hole, it would give us a transformation of functors. When I put this circle in here, I will have a transformation from the category. This was the category associated to a point. I will get something from the category associated to the empty set tensor that when I put a hole in it like that. And this is just the category of vector spaces. So I will get on each object of the category, I'll get in, sorry, I said that rather badly. Each object of C acquires an action of A, this generalized semi-commutative algebra. Now, I think that the general philosophy is that this is a very good notion, this framework, where this plays the role of the additive category of non-commutative geometry, and they play the role of modules over this not quite commutative ring. That's a more rigid, it's on the one hand loosened because these aren't even associative algebras, but it's more precise than the Kohn theory in the sense that we have approximate commutativity. Now, just to try to conclude by the difference that makes. You see, one of the things that might make you think this whole project is rather crazy is that suppose you take one of again Kohn's examples is suppose you take a finite dimensional compact manifold M and look at its cotangent bundle. So think of that as a locally compact space. Then if we look at the algebra of functions on this, vanishing at infinity, and this will be the algebra which corresponds to vector bundles trivialized at infinity on the cotangent bundle. They will be the symbols of differential operators acting on functions on M. So this is sorry, it should be 0. This is a nice object of non-commutative geometry. But it has its standard deformation into compact operators on L2 of M. So if you just look in the non-commutative geometry framework, here we have this algebra, and whatever we associate to it is going to be the same as what we associate to that. In the case where this was R2 or something, this was the Stone-von Neumann deformation I talked about before. So that would be saying that this thing seems to be looking like a point up to deformation in non-commutative geometry. Now, that is, of course, the way Kohn looks at the index theorem, because he says the K-theory of this will be just determined by some integer invariance, and when we think of the element of K as being an operator here, then we'll think of it as just giving us a vector space, a module over a point, and that will just have its dimension, and all we will see of the operator is its index. So in the non-commutative geometry framework, you see, we seem to be killing far too much, because every compactified cotangent bundle is going to go to a point. In other words, whenever you have a Poisson manifold, you effectively collapse all its symplectic leaves. So I think you definitely aren't going to get a description of the universe just from non-commutative geometry. You have to put in some more refined structure, and I think this is a very reasonable candidate for the best way to say what the refined structure is that will keep more of which will distinguish between just, say, the linear algebra of the Dirac operator on a manifold, say, which tells you its index, its A-roof genus, and the actual amount of geometry which we expect to be able to see about the universe. Well, now I'll stop. It's time to stop.